Our speaker today is Sam Hughes from Oxford, who is going to tell us about torsion homology growth and related topics. Take it away, Sam.
Thank you for the invitation. This isn't quite topological complexity, but hopefully there's some overlap if we get far enough. Everything I'm going to be talking about is based on joint work with Sam Fisher, who's a student here, and Ian Leary, who's a professor at Southampton, who I'm sure you're all familiar with. Okay, so there's going to be some group theory, and then there's going to be some topology, and then it all comes together, and maybe there's something of a story involved. So, okay. Also, if I write too small or you have any questions, just interrupt. So G is going to be a finitely generated group throughout. And we say G is residually finite. Which I'll probably denote by res fin from here on because it takes a while to write. If the intersection of all finite index subgroups of G is the trivial group. So here we just have H, finite index in G, H equals trivial. So this is kind of equivalent to there's some finite quotient of your group where you can send that element to the non-identity for every element, and the quotient depends on the subgroup or the element. Okay, a chain is going to be a nested sequence of finite index subgroups. Of G. So we denote this by Gn like this. And you can think of this as G equals G0, which is going to be then have in it finite index G1, and then in that there'll be some G2, and this keeps going. Usually we'd index over the natural numbers. So and then we're going to say a chain is residual. If firstly Gn is normal in G, and the intersection of these Gn's is the trivial group. So this is kind of the standard object, and this will at some point eventually correspond to a sequence of regular covers of some space. That's the idea. So kind of a very easy lemma that we may as well prove. If G is finitely generated, residually finite, then there exists a residual chain. It's just a gentle warm-up. This has been a long week for me. So this is quite easy to prove. So we'll just do it. This is kind of a standard fact, I guess. The proof is simple. You let Gn be the following intersection. It's going to be all index n subgroups of G, and you just intersect them all. Now, this is actually a characteristic subgroup of G. So Gn is characteristic. So that implies Gn is normal in G, and it's finite index because it's an intersection of finite index of groups. So we can just write finite index there. And then to prove the other thing, which is the intersection of all of these Gn's is the identity, well, you just play around with the intersection. So you look, you got n greater than or equal to 0 of Gn. It's just going to be the intersection of n greater than or equal to 0 of these intersections of G colon H less than or equal to, sorry, equals n, H less than or equal to G. Actually, I probably want less than or equal here. Excuse me. H, and then this equals the intersection of just all finite index subgroups of G. But G is residually finite, so that's the trivial group. Okay, a nice easy lemma. So we know this exists if G is residually finite, so that's good. So now we can kind of move to topology. So we're going to let X be a compact connected CW complex. We're going to suppose G is residually finite, so G equals pi1x is residually finite, and we're going to have some residual chain, Gn is a residual chain. So now we can let xn onto X be the finite cover corresponding to each Gn. So here the quotients acting as Dirac transformations. I know this is a regular cover, but it's going to behave as well as you could hope from the point of view of covering spaces. So basically the motivating question is that I want to understand how Betti numbers or how homology made into some numerical invariant grows through finite covers. So this could be like you take like the sequence of Betti numbers scaled by the index of the cover, something like this. Or you take like mod p Betti numbers, or you take like the log of the torsion. So the goal is just to understand these invariants, basically. So we want to understand lim sup as n goes to infinity of, say, the Betti numbers of xn with coefficients in some field. And we want to scale by the index of the cover, so G colon Gn. And then there's like kind of a bunch of natural questions that immediately come up. So firstly, is this a limit rather than just a lim sup? Does this depend on the residual chain? Can we compute it is another question. There's kind of natural things that you might want to ask. Do these numbers tell us anything about the group or the space? Do these numbers have applications? So that got a bit messy. I'll just write it underneath. So I'm hoping that I can answer all of these questions, some in special cases. So let's just look at one quick example. Just so we get a kind of a flavor of what's going on. So if we have x equals s1, which is this here, this circle with one cell and one 0 cell, well, we can have gxn equal to you draw this with n1 cells now. And then 0 cells. And maybe actually we do like 2 to the n, just so they're nested, something like this. No, n's fine, n factorial, there we go. That works, okay, good. So now we can look at the limit. Well, this is as n goes to infinity, we have b1 of xn, say some field coefficient, and we're going to scale by the index, which is n factorial. Actually, we can put an m here. But this equals the limit then goes to infinity of the Betti number of the circle in your favorite coefficient system, so that's 1, and on the bottom you've got n factorial. So that equals 0 for all n. So here, in this very easy example, in this one case, in this one set of covers, we've shown that this limit actually kind of is 0. Okay, so anyway, Wolfgang Luke comes along in the 90s and proves something very remarkable, which I think is slowly kind of gaining more attention as time goes on. In 1994, he proved his now famous Luke approximation theorem. And this says when you take rational coefficients, this is actually a limit, not a lim sup. And it doesn't depend on the chain. So here, Bm of xn with q coefficients scaled by the index is going to equal the nth L2 Betti number of x. Tilde the universal cover with G acting on it. So remarks, this is a limit, not a lim sup. So it's better than a lim sup, I guess. So yeah, one kind of, it's a special case of the other one. So not just, it's probably more appropriate. And secondly, this does not depend on the chain, on the choice of residual chain. So this is good. Now I need to tell you what this is. So that's going to be the next part of the talk. So what is this mysterious L2 Betti number? Well, BM2 does not have a very nice definition, unfortunately, unless you've read Luke's book, and then this isn't so scary, but basically it's the dimension over some strange algebra associated to the group called the group von Neumann algebra of the equivariant cohomology of x tilde with coefficients in the group von Neumann algebra. And basically the point is this just lives in 0 infinity, like this. So this is the nth L2 Betti number of G acting on x tilde. And you can think of this as of x, if you prefer, where this is x tilde mod G. Okay, so maybe at this point, because I've just introduced this strange thing and I haven't told you what the group von Neumann algebra is, and I don't really want to because there's only an hour here. I will instead tell you some properties of these things and some applications, and instead maybe this will kind of motivate why you would care about these things. So properties of L2 Betti numbers. So the first thing is that they're multiplicative. So BM2 of x tilde with coefficients in G is going to, coefficients in H is going to equal the index of G and H times the nth L2 Betti number of x tilde with coefficients in G. And here H is a finite index subgroup of G. It doesn't need to be normal. Secondly, the Euler characteristic of X is equal to the sum, I say n greater than equal to 0, minus 1 to the m. But instead of the ordinary Betti numbers of the number of cells in the chain complex, you can actually put the L2 Betti numbers in, and you still get the same answer. So here x tilde and G. So they're like Euler characteristics, but more precise in some way at the moment. So that's kind of cool. They obstruct X being homotopy equivalent to a mapping torus. So if you care about, say, manifolds fibrin over the circle or these kind of questions, finite CW complex. So if you kind of care about these fiber hyperbolic manifolds or this kind of thing, you need to know, like L2 homology is the first obstruction in some sense. So you go check this first. So this is kind of this has applications to a huge amount of natural questions, and like a lot of the research I think about is really related to when this happens, which is kind of where my motivation has come from with a lot of this stuff. It also obstructs S1 actions, which I don't really know about, but this is true. So I think Luke proved both of these at some point in the past. He certainly proved this one. And also the L2 Betti numbers of an amenable group. So you just take your CW complex to be BG or KG1 if G is, when G is discrete of an amenable group vanish. So you have some kind of nice vanishing results there. Okay, so they're kind of cool. They have some applications. There's a lot more I haven't mentioned. They're incredibly powerful when you're doing group theory, so that's really useful. So they kind of show up quite a lot, I guess, in my line of work. So then I guess now we can define mod P L2 Betti numbers. So this is going to be B M2 G, a residual chain, and then a field is going to be the limb soup. It then goes to infinity of Bn Gn with coefficients in F scaled by the index. So this is kind of you've taken the Luke approximation theorem and you've just made it into a definition, and all the questions we were asking earlier now just make sense in this context. When it's independent of the limit, I'll drop this bit, like from the notation, so it's implied that it's independent of the residual chain. Okay, so Luke conjectured in about 2010. I'm not sure exactly when it was first wrote down, but around 2010, Luke conjectured the following: that B M2 G GNF is actually just going to be equal to the L2 Betti number of G. And again, he conjectured this for spaces, aspherical spaces. So there were counterexamples if your space wasn't aspherical. So this is in the 2010s. And then kind of a disaster / theorem due to the Avramedia and Shriver. So this is Grigori Avramidi, Boris Oken, Kevin Shriver, which just appeared in Invent Math. They disproved the conjecture. And the example is extremely explicit, in fact. So this just appeared. So they proved that BM3 AL with coefficients in F2 equals 1, but the third L2 Betti number of this group is 0. This requires a bunch of remarks. So this one is actually due to Davis and Leary. So Leary of my collaborator, / PhD advisor on the title, and Mike Davis, who's you're probably familiar with if you've looked at Coxeter groups and things like this. And now here, L is a flag triangulation of RP2, just the real projective plane, and AL is equal to that has generators the zero skeleton of L, and then relations X and Y, if and only if X and Y span a one simplex. So they're contained in the one skeleton. So it's just some group. It's called a right angled outing group. If you've not seen these before. Okay, so you might think that this is the end of the line, but there's one thing to note. This here is independent of the chain. So they proved that it converges to something independently of the chain, and it's just number one. And that's kind of interesting because maybe there's some hope. Maybe we can find a different homology theory that's defined over F2G that gives us the right answer. So this is kind of what the next part of the talk is about, which is I'm going to describe a new homology theory which gives you the right answer in this case. And then I'm going to conjecture it for a bunch of more groups. And then I guess we'll probably roll credits because that's kind of where we got to. And there'll be a little bit about amenable categories this time. Otherwise, I've planted a question for the audience. So that's good. Okay, so wrong color. So we're going to let F be a skew field. So you should think of F2 or FP really, but any finite field is really the canonical example, but this kind of works more generally. I just want to emphasize that. So Heiken, Zapparain constructed some cool rings. This is a single dash in LaTeX, not a double dash. So it's one person. So Heiken basically showed that if G is what's called locally indicable, which again I'll explain in a moment. But this is like a very big class of groups. This is kind of like like most hyperbolic manifold groups have this property, and that's kind of the natural examples for geometric group theory, and also lots of other stuff do. So like many hyperbolic groups, things which don't have property T, other things. So if G is locally indicable, then there exists a Hughes free, not related to me in any way. Hence the free part. No, just a joke. There exists a Hughes free division ring. FG, which FG embeds into, which we're just going to denote by curly DFG. Okay, so let's kind of give some explanations. So this blue thing, this means that for all H subgroup of G, either H is the trivial group or H such X onto Z. Oops, very messy. H just has a non-trivial first cohomology class if you prefer, with integral coefficients. And then this yellow part is Hughes free division ring. Well, this says, well, I won't tell you what this is because it's technical, but you should think of it as like a field of fractions, except for it's much bigger. So most groups don't have a field of fractions when you take that group ring, but you can build a much bigger ring which behaves like it. So this is sort of like frac FG if it existed. But it's much bigger, and it has some universal property. And the other important fact about it is that it's unique up to FG isomorphism. So in some sense, it's also canonical. So like it's got a lot of nice properties, basically. There's only one of them up to a reasonable choice of isomorphism. So it has a universal property, which is kind of a pig to write down. But it, it's kind of behaving in some sensible way. And there's one more thing we should mention, which I will get to in a moment. But first, this is a G module, so you can just compute homology or cohomology in it. So we can compute the following things. Well, first of all, we can compute homology. So we'll denote this like this. FG, FG. You can do this for spaces too, you just take equivariant cohomology. And this is just going to be kind of chain complex of EG, tensored over FG with DFG. So it's kind of what you'd expect to want to compute. And obviously you can put any G space here if you want to. But just for the kind of simplicity of this talk, we'll stick to groups. And similarly here, we can define Betti numbers. And now the thing is, skew fields are basically fields. They're not quite, because they're non-commutative, but they have canonical dimensions, and those dimensions are integers. So these Betti numbers are super nice, because they're just the dimension of this homology group taken over as modules over the skew field. So it looks like this. And these live in 0, infinity. Well, actually, sorry, they don't even live in there. They live in z greater than or equals to 0, union infinity. So they're like super nice. They're kind of like ordinary Betti numbers. We're back into integers, so this is good. And they have loads of properties that are suspiciously similar to Betti numbers. Now, if I had a blackboard, I'd have gone over to the blackboard and I'd have put them side by side. And if I could make my tablet go landscape, I'd also write them side by side here, but I can't do either of those. So you're just going to have to believe or remember from earlier. Okay, so properties of these DFG Betti numbers. So there's a few good things. Firstly, they're multiplicative through finite covers. So that's what we want. That's good. So BM DFG equals G colon G. Cool, sorry, missed out the argument, equals G H of BM DFG of G. So that's good. So this is due to one more thing, H, finite index in G, and this also works for covers. There's nothing kind of fishy going on there. So this was proved by Fisher from above, I think last year, but also Haneke and David Kilak kind of basically proved this already in like 2018, I think. Okay, so this is good. Similarly, the Euler characteristic behaves the same with appropriate finiteness properties. So if we take the alternating sum of these guys, we get back our Euler characteristic. So that's good. And again, you can put a space in and look at the quotient and everything's what you'd expect. They obstruct map in tori. Like above. I think it's conjectured they should obstruct S1 actions as well, but I don't know for a fact. This is true. They vanish on amenable groups. And really, to kind of drive home the analogy, in fact, Linnell, much earlier, before these were really introduced as a formal thing, Linnell proved that dQg of G, and again, any G space, is actually just equal to the L2 Betti numbers of G. Linnell proved this in the 90s, I believe. So you actually recover L2 Betti numbers. So it really is a generalization for these groups and their appropriate G spaces. So then we can make a really kind of obvious conjecture now. Once you've put all of this information together, it's kind of screaming to be conjectured. So Fisher, H, and Ian, this is kind of the main theorem of this talk is just a conjecture, and then some evidence for it. But if we take F skew field, G residually finite of type Fn+1. If you don't know what this is, just think of a finite kg1. This is just saying you've got finite kg1 into the n+1 skeleton, such that this ring exists, and let Gn be a residual chain. So kind of just the set that we've had all along. Then the conjecture is that this homology gradient sequence in this chain with the coefficients in the skew field, well, this is exactly going to be these DFG Betti numbers. Okay, so that's the conjecture. So I can hear you all going, well, what about rags? Because you told me they were the counterexample to the original conjecture. So if your conjecture doesn't hold for rags, then it's rubbish. So that's kind of our first theorem. FHL, say 22 plus, hopefully on archive this year. The conjecture holds for the following. So it holds for right-angled Artin groups. Oops. So you go, okay, good. You've ruled out the obvious counterexample. What else? Well, the classic kind of group theory counterexample to homological questions are best in Brady groups. So we thought maybe we can prove it for that too, because they behave in a similar way to rags. Once you understand rags, you can understand the level set, and like you can throw spectral sequences at this thing, and maybe you can compute stuff. So we worked quite hard, and we could do Artin kernels, which are slightly better than Betti and the Brady groups. So here, Artin kernels are defined as follows. So this is the kernel of a map which goes phi from AL onto Z, like so. So just any of these maps. And this includes Betti and Brady groups. So we've ruled out the two big counterexamples for homology questions within groups, so that's good. Of course, here you have to assume they're of type FPM over F. So actually, we don't even need to go up to n+1. We can just get FPM. So we're really on the nose. And we can also do graph products just by generalizing the Artin kernel argument. So this is graph products of amenable Riefers groups. I'm not going to talk much about this because it's kind of technical, the condition, and maybe not enlightening at all. But this is just kind of the method generalized for rags, basically. So we just added this. So I won't comment too much on the proof. It basically just builds on a lot of other work that many other people did. So this is like comments, I guess. So it's by several, I think that's how you spell several soul searching spectral sequence calculations. Now, when I was a bit younger, I probably would have tried to have done these in a talk, and famously maybe in about 5 minutes. Most people don't really respond well to this. They don't invite you back, so I won't do that today. Instead, I'll tell you where to look to get the idea of how you might do these. So we do several soul search and spectral sequence calculations for each invariant. And the ideas for these come from a number of places. So this is based on work of Davis Leary in 2003. So that's where they computed the L2 Betti numbers of Artin groups. Davis Oken, so they compute the L2 Betti numbers of Betti and Brady groups. and other things. Then Avramidi, Oken, and Shriver, so that's the paper from earlier. Where they compute the mod P homology gradients of right-angled Artin groups. And then Oken and Shriver, where they compute homology gradients for some more things, and we kind of adapt some of their methods. Okay, so this has gone a lot quicker than I expected it to. So maybe I will talk about amenable theory a little bit more, because there's some more evidence. Because I don't really want to kind of start whipping out equivariant Majorana sequences that, yeah, it won't be enlightening, I don't think. So instead, let's move onto cat amenable. Okay, so now X is a path connected space. And we say Q, the subspace of X, is amenable. Note U isn't necessarily connected. Only X is path connected. U can be a bit of a mess. So U is amenable if for all X in U, pi 1 of U comma X to pi 1 of X comma X has a amenable image. Maybe I should say what amenable means. And roughly it says that there's a G invariant mean on the group, where a mean is like a measure, a measure. So these are kind of things like polycyclic groups or abelian groups. Conjecturally, or depending on who you ask, maybe Thompson's group F is still a wide open problem about this. Kind of, you can do like, you can take the class, you can take all finite and abelian groups, and you can take the class generated by their extensions, their subgroups, their quotients, and their limits. So you can get huge groups showing up in this class, but they're all kind of built up out of these things. So it's quite a big class. And this kind of is one of these generalizations of Lustenich-Neumann category that the 7R is kind of around. So hopefully you're all familiar with this and I don't need to labor it too much. But yeah, so a little prop. If so G, FG as above, but G is now just type F, and DFG exists, etc. So if cat amenable of G equals K, then these DFG Betti numbers, oopsie, DP, DFG of G is going to equal the homology gradients to GN, coefficients in F. And these are actually going to equal 0 for P greater than or equal to K minus 1. I haven't told you what amenable category is, sorry, I completely forgot. We'll scroll back up in a moment. The amenable category of X denoted cat AMN of X is the min n in n cup infinity such that there exists an open cover of n of X by n plus 1 amenable subsets. Okay. You might prefer multiplicity, and then you have to normalize slightly differently. And this n+1 is why there's a k-1 here, basically. Okay, so now we know what that is. Let's go back up. So if we have this DFG Betti numbers existing, G is residually finite and type F, then actually the amenable category makes both invariants vanish. I should mention that Roman-Zauer proved, proved this. So Roman-Zauer proved this kind of equality here, and we sort of observed that his proof adapts. So, although Roman only proved it for aspherical manifolds, if you kind of read into it, you don't need the manifold hypothesis at all. You just need a aspherical CW complex. So this is kind of a bit more evidence that maybe you'd expect this all to kind of behave similarly. And then we use this to prove some stuff about minimal volume entropy, which is kind of another same flavored idea in this kind of flavor. And basically, it all behaves the same. So, which is kind of, again, more evidence, like somehow if you could show one of these things didn't work, then our conjecture would be false. So maybe these theorems are all accuracy true because these things are the same, and we're just kind of gathering evidence for it. So using this, we could kind of show some stuff about minimal volume entropy, and notably we could prove, well, maybe I'll tell you what it is first. So X is a finite CW complex with piecewise Riemannian metric G. X naught is a base point in the universal cover, and G tilde is the pullback metric. So piecewise Riemannian metric is just a metric when you restrict to the interior of a cell, it is Riemannian, and then maybe it gets a bit singular on the boundary. So then the volume entropy, there's like three definitions that kind of build on each other. So the volume entropy of X is ent xg, so it really depends on G as well. And this is kind of just the volume entropy, what you might expect. So you look at increasingly big balls centered around this base point in the universal cover with this metric, and you just scale by the size of the ball. So it's kind of looking at how balls grow once you scale by how much you've expected it to grow. So then the minimal volume entropy, similar, but now we're allowing the metric to vary. So the minimal volume entropy, true. So this should really be xg, shouldn't it? The minimal volume entropy of X then no longer depends on G, so we call that omega X. And this is defined to be the infimum over G, the entropy of xg. But now we have to kind of normalize. So we do something like divide by the volume. Oh no, we times by the volume of xg, but we scale by the dimension of X. So this is looking at kind of the smallest possible metric and how that grows. This is what this is doing. So G varies over all metrics. G varies over all metrics. All of these piecewise Riemannian metrics. Then if G is a group, we can define its minimal volume entropy. So here, the minimal volume entropy of G is omega G, and this is the infimum of these omega X's, where X is a kg1 and the geometric dimension of it, or the dimension of X, I guess. Dimension of X equals the geometric dimension of G, which you can think of as cohomological dimension if you go to dimension 3 and above. So not so bad. Okay, so this is like, as you can probably imagine, horrifically hard to compute. So the results that are really known are kind of due to Matthew Hallmark, Kevin Shriver, Corey Bregman, and Matt Clay, and then Kevin Lee. So Corey and Matt computed this for some free bicyclic groups and two-dimensional rags, and then Hallmark and Shriver proved when it's non-zero for some more rags, and then Kevin gave a characterization of when it's non-zero for all rags. So it's kind of known for rags and free bicyclic groups when it's non-zero. So we kind of used these ideas, and basically we showed that kind of a corollary of above, once you read the literature, this is kind of a one-line proof. If G F above as above, and G is type F, we have, oh, and we need one more condition, G and G has uniform exponential growth. I'll explain what that means in a moment. So let, I guess, if B M DFG of G is non-zero for some M, then this thing is bounded away from 0. So we get the same result. This was known for BM to GF. That was Hallmark and Shrevey this year. So we've kind of recovered this, which is kind of, again, it's just more evidence for the conjecture. It's not going to prove anything, but it could have given a way to disprove it. So this uniform exponential growth is kind of funny to me because it has a few names in the literature. So one of them is uniform exponential growth, which looks like a typo, so that's not great. And then the other one is locally uniform exponential growth, but a local property is something that's held by all subgroups, and exponential growth can never be a local property because abelian subgroups wouldn't have exponential growth. So the two definitions in the literature, one is wrong and one's a typo, so that's good. So we've changed it to uniformly uniform, which looks slightly better. I hope it catches on. Yeah, so this is kind of where we're up to. We have some ideas about how we might try and prove various bits of this conjecture in the future, but we don't have a general strategy at the moment. So if this takes your fancy and you want to kind of find more invariants which interact with these categorical invariants and do some cool homology calculations, this was my sales pitch to try and get you interested. So thank you for listening.
Thank you, Sam. Any questions from the audience?
I could have a question.
Go
Hi.
on.
Can you hear me?
Yes.
Yeah. So, hi, Sam. So you said that a group is locally indicable if a non-trivial subgroup surjects onto Z.
Yeah.
Is that right? And then you said that if it's locally indicable, you can define this DFG.
Yeah.
But then you said that existence of DFG Betti numbers obstructs being a mapping torus. And I'm kind of confused because I thought like surjecting onto Z is pretty much the same as being a mapping torus.
No.
So what am I missing?
So the kernel will have some bad finiteness property at some level.
Okay.
A finite CW complex.
Yes.
Yeah, so there's like a small subtlety there. I actually made a mistake. So it's conjectured that they exist for locally indicable groups. They do exist for the subclass of rationally solvable residually finite groups, which is kind of most locally indicable groups that we understand. So, and a lot we don't, because it includes all, like, conjecture includes all hyperbolic manifold groups. But I think Hyken has a fairly strong opinion that they should exist for locally indicable. And you can extend to finite index over groups, but you can't, even with torsion. So this ring can never exist if you have torsion in your group, because you're embedded into a ski field. But somehow, like, kind of natural geometric groups are often locally indicable, so it's not such a bad hypothesis. Excuse me. And it exists over Q always for locally indicable. That's what I can actually prove that too.
Ah, okay, thanks.
Which is why we expect it exists for more stuff, basically.
Okay, thank you.
Mark, if you had another comment, it just broke up on us.
I
Okay.
didn't. I'm just walking home. Sorry. I'll mute.
So good.
Any further questions? If not, I will stop the recording. You can ask more questions informally if you're so inclined. Let's thank Sam again.